Morning, everyone. So I'm going to talk about close-in exoplanets, and particularly ones that are evaporating quite vigorously. So why is this interesting? Well, observational studies of exoplanets now have been growing dramatically over the last 5 years. And what they've shown is that one dominant population of exoplanets is exoplanets really, really close into their central star. So the left-hand plot there is the radius period distribution from one of the latest Kepler NASA telescope data sets. And what you can see is there are clearly sort of thousands and thousands of planets very, very close to their central star. Perhaps the more surprising thing about this is if you look at the plot for the few that we have mass and radius data for, so that's the plot on the right-hand side, what you can see is that they have quite large radii for low masses if you were to think of them as rocky planets. And the interpretation is that they actually contain a significant hydrogen-helium envelope. And the statistics from the left-hand plot is that, on average, each star contains one of these very, very low-mass planets with a significant hydrogen-helium envelope. So one really has to think, what's going to happen to these very, very close-in exoplanets with these very, very tenuous atmospheres when they're so close to their central star? So one interesting thing is that at early times, for the first 100 million years of their lifetime, young stars are extremely luminous in the X-ray and the UV. They're about 10 to the 3 times brighter than our current sun. And that lasts is basically continuous for the first 100 million years of the star's lifetime. But this also corresponds to the time when any tenuous hydrogen-helium envelope is much, much larger. It can be almost a factor of 2 to 5 times larger in this early time. So what you can do is you can write down a simple energy argument where you can look at the binding energy of a close-in, tenuously bound atmosphere to one of these exoplanets and compare that to the kind of energy you receive in these X-rays and UVs. And you can see in the bottom left there that the energy you receive in the X-rays and UV is certainly significant to make any kind of any kind of evolutionary consequence interesting. And the other interesting thing is, at these such high fluxes, you can actually heat the upper atmospheres to roughly 10,000 Kelvin. And you can also get it in the case where it's so high density that the gas remains fully collisional and in the hydrodynamic limit. And you can actually drive evaporation via a so-called transonic wind, where you start off subsonic and you actually go through a sonic point and you completely leave the atmosphere above the escape speed while still remaining hydrodynamic. So to study this, we set up a bunch of simple 1D calculations a couple of years ago, where what we did is consider the streamline that connects the star and planet. And for these close-in planets, you can actually show that the Coriolis force is about a 1% correction to bending the streamline, so we completely ignored that, and just solved the radiative transfer and hydrodynamic problem along that simple streamline. Then, once you have that solution, that hydrodynamic solution, you can obviously check that it's still in the hydrodynamic limit, and then you can times by 4 pi r squared to get your mass loss rate. So it's quite crude, but what it allows you to do is fully explore the full parameter space that we see observed exoplanets in. So the left-hand plot is a plot of planetary mass versus planetary radius. And what the color map shows is the mass loss rates we obtained from this exercise. So the gray region to the right is the region where any planet would be so big it's overflowing its Roche lobe, so it's not really a planet. And the white region to the right is where we calculated the solution, but when we went back and checked it's in the hydrodynamic limit, we found that it wasn't. So what you can see is you get a large range of parameter space that really does remain in this hydrodynamic limit. So the points observed exoplanets. The magenta dotted dashed lines are lines of constant density, so Earth-like, which is about 5 grams per centimeter cubed, Jupiter-like, about 1 grams per centimeter cubed, and these very, very fluffy things that low mass cores with a tenuous envelope of about 2.2 grams per centimeter cubed. And then the faint dashed lines is probably the most interesting line. This is the mass loss rate times a time. So we're taking it's a giga-year and 100 million years here. And what you can see is any points to the right of that would have been completely destroyed by this evaporation. Any points very, very close to the line, evaporation is going to be a dynamically important effect. So if you look in the bottom left at low planet masses, you can see that the points are starting to get very, very close to these dashed lines, which is telling you that evaporation of these atmospheres is going to be very, very important for their evolution. So as well as just doing one set of orbital parameters, we also changed a large set of other parameters. So we varied the X-ray luminosity of the star and the UV luminosity of the star. We varied the separation. So you can see these color map regions moving around. And you naively get what you would expect at higher X-ray luminosities, and the fact if you're closer to the star, you get higher mass loss rates, but you also get a larger region over which you remain in this hydrodynamic limit, and you can really get vigorous mass loss. So the next step was to couple these calculations to models of the planet's evolution. Obviously, you want to understand how this evaporation might sculpt and affect this big exoplanet population. So the first discovered exoplanets were these hot Jupiters, and when they started finding these low-mass exoplanets that were very close to their star, there was a suggestion that perhaps these low-mass exoplanets could be evaporated remnants of hot Jupiters. But you can see in the left-hand plot that's clearly not the case. So this is the evolution of a Jupiter-mass planet, very, very close to its star, almost obscenely close to its star. It's in a period of about 3 days, so obscenely close. And the amount of mass it loses is very, very low, about less than 1%. However, if we go to one of these low-mass planets, so this is an initially 20 Earth-mass planet, each of the different lines corresponds to a different guess of the initial entropy of the planet. We have very little information as to what the initial entropy of these planets are, so we just have to guess and run a bunch of models. But you can see in the bottom left plot, which I think is just cut off, that is mass versus time. So you can see that the planet loses a huge amount of mass. In fact, it loses almost all of its envelope in this case. So it has a 12.5 Earth mass core. So it's almost lost its entire envelope. The bottom right plot shows when that's happening. This is mass loss rate times time. So you can see it's happening in this first 100 million year phase when the star is really at its X-ray brightest. And the two little arrows in the top point are basically where you would end up if you didn't have this evaporation process. So evaporation in general, as you would expect, makes a planet smaller and more dense. And finally, you can look at how this changes with separation. So these are, and each line is initially the same initial planet, and we're moving in with separation. And you can see that as you get closer and closer to the star, and the transition's about 0.2 AU, once you come inside 0.2 AU, evaporation starts to dominate the evolution of these close-in exoplanets. And if you go in too far, so maybe sort of 0.05 AU or even a bit closer, 0.03 AU, you can actually completely strip these planets of any initial hydrogen-helium envelope and just leave a bare rocky core. So that's quite a dramatic effect. So we can see, can we see any evidence for this in the observational data? So the plot on the right here is the observational data, but now it's not the first plot I showed you. Initially, it's a subsample, so it's subsampled by type of star. And the reason that's important is the X-ray and UV properties of stars vary dramatically. So if you want to sort of try and tease out any effects of individual stars through individual models, then you need to pick one type of star. So you can see a clear sort of decline in very, very fluffy planets as you get closer and closer to the star. So what we did is we built a rough synthetic model where we picked an initial planet mass of about 20 Earth masses, and then we varied it all the way down to very, very low masses, and we also picked a range of core masses, so the colors in this plot represent different core masses from 15 Earth masses to about 3 Earth masses. And each same colored point in the sort of y-axis represents a different initial hydrogen-helium envelope fraction. So when you pick this initial set, you get a reasonably rough, good agreement. So the argument is that this sort of fall off in very low mass, large radius, low mass planets is primarily driven by this evaporation. And once you get very, very close in, you can actually completely strip these exoplanets. And any rocky world that's very, very close to its star probably had a hydrogen-helium envelope to start with. So 1D models are nice. So what we've been working on lately is building multi-dimensional calculations. So we've developed a new code to do this. So our flow, we think, is going to be roughly spherical. So we build the hydrodynamic grid on a spherical grid. But obviously, we've got to do this plane parallel radiative transfer through it. So we've come up for a method to do that. We do the UV and X-ray radiative transfer. We do time-dependent heating and cooling and ionization and recombination. So this was one of our first calculations just to sort of try and assess how good our 1D models really were. So this was a 2D model. So the stars to the left in this plot, and the white region is basically the planet that's been removed from the calculation, and the sort of thin, tenuous colored regions are this initial envelope. And then we switch on the star, and we drive this hydrodynamic flow out. You get a subsonic wind that drives to the night side of the planet, which is very interesting. And what that night side wind does is that it actually allows significant mass loss from the back as well. So we actually found that the 2D mass loss rate was actually pretty close to the 1D mass loss rate due to this night side advection. Another complication is that we all know that planets contain magnetic fields. So if you look at the flow geometry, which I've now flipped, so unfortunately the star's to the right in both these plots. Now the flow geometry is basically radial from the equator and parallel to the planet's atmosphere at the top. But if you compare that to a magnetic field structure, a dipole magnetic field structure is obviously parallel to the atmosphere in the equator and radially outwards at the top. But given this flow is going to be highly ionized, it's going to strongly couple to this magnetic field. So you have two choices. Basically, the flow's got to blow this magnetic field structure out, so you get a radial flow and radial magnetic field, or the flow is going to be forced to follow the magnetic field line. So this was an initial calculation. Again, we picked a Jupiter mass planet, we put it really, really close to the star, and we put a tiny field on it, 0.1 Gauss. So Jupiter's 5 Gauss. Really is an experiment to see what regime we're going to sit in. Are we going to sit in the magnetically dominated regime, or is the flow just going to blow this field structure out? So if I switch it on, what you see is the flow does blow the field structure out slightly, but you still retain a strong dipole structure close to the planet. And given we've picked quite low parameters, we've tuned everything such that the flow really could be able to open out this magnetic field structure, we suggest that flows from hot Jupiters probably are strongly magnetically controlled. And that means that the flow is highly suppressed, because you're not getting the flow from the equatorial regions due to this dipole structure. So one final thing is the magnetic fields can also lead to variability. They can actually suppress transonic outflow. You can set up your field structure such that you can't get transonic outflow, and that leads to variability. So we've done that in this picture here. So the polar regions are set up such that you can't get transonic outflow, and what you see is you just get variable outflow in the right panel, where the flow is outflow sometimes and then falls back in. So, in conclusion, evaporation can be really important for these very low-mass planets. It can completely strip hydrogen and helium envelopes if you're close enough, and flows from hot Jupiters are likely to be magnetically controlled. So, thank you.
Questions?
In the case that you allow for a magnetic field of the planet to exist, you need to embed this magnetized planet in the stellar wind surrounding the planet. How are you going to know that magnetospheric?
Yeah, so in these calculations, we just have a very crude picture of the stellar magnetic wind and stellar magnetic field, and we actually just, these planets are so close that they're actually inside, can be inside the dipole structure of their star. So for all the magnetic calculations I've showed, we've just got a vertical field that represents the star.
But then you have effects like magnetic reflection and so on. What is the completely changing?
Yeah, so
Do you allow for reconnection?
we do allow for reconnection, although it's numerical.